Okay, hey y'all. So we're gonna go ahead and do this fun worksheet here, which talks about, the first question is about a good nucleophile. So before we do that, let's go over what makes a good nucleophile. So remember, nucleophiles are things that love positive charges. So a good nuke is gonna really love a positive charge. The other thing that we kind of discuss with nucleophiles is that they have to like get into some pretty crazy places. So good nucleophiles tend to be less sterically hindered. In order for them to love a positive charge, I probably should have added up here, they're going to have a lone pair, a double bond, or a triple bond. So they've got to have some kind of pi bond that they can offer, and they have to have or they have to have a lone pair. They love to have negative charges. So if you have a good nucleophile, it's going to have a negative charge. If it's a strong nucleophile, it has a negative charge generally. They like to have low electronegativity differences. This is something we didn't cover too much. But let me give you an example. Like if something's bound with phosphorus or sulfur, it's going to be better than something more electronegative like a nitrogen or oxygen. This is counter kind of to the bases that we've encountered. Another example of this might be like if you have like an HS negative versus an OH negative. Generally, we use this as a nucleophile because it's a fine nucleophile. It does its job, but this would be a much better nucleophile. Again, because S is less electronegative. And polarizability is another factor that affects nucleophiles. So what that means is that if they have an electron cloud kind of around them, that electron cloud can distort, and it can distort best when you have big atoms. So this tends to be with bigger atoms tend to be more polarizable, specifically like a sulfur or a selenium versus an oxygen. Again, this is because these are bigger things that have bigger electron clouds around them. And these electron clouds are more malleable than, say, something really tiny like a fluorine or an oxygen. An example of this might be like I- is a better nuke than F-. Again, I- is just really big and F- is just really small. And we talked about in class, we just talked about in terms of size. Then we have bases. So generally speaking, a strong nuke, or I should say a strong base, will be usually a strong nuke. So generally a strong base is going to be a strong nucleophile. But there are cases where that's not true. So for example, if you have something like I-, versus CN-, all right, I- here is a very weak base. It's a weak base because if you took its conjugate acid, HI, you know that this is a strong acid. And therefore, I- must be a very weak base, right? So this is a really weak base, but it's a good nuke. So just keep in mind that there can be exceptions like that. So let's see what else. I'm looking at my notes. Steric hindrance, and we already covered steric hindrance. All right, so these are kind of the main things that you look for when you're looking at nucleophiles. So let's talk about this question now and see if we can use what we just discussed to make some sense of these answers. All right, so OH-, like we said, that's a decent nuke. We'll just put decent or okay. It's not great because if it was an SH, like we said, that would have been a super strong one. All right, and then we get to this one right here. Anytime we have selenium, because that thing is so big and so malleable, it can get into those spaces. Its electron cloud can kind of move and change. We call that polarizability. This is actually a great nuke. Again, because it's polarizable. And that's just because it has selenium. Again, selenium, sulfur, those will be kind of the bigger atoms that are going to be a lot better. Iodine, etc. All right, here we have an Se and a negative. This is a wonderful nuke. Again, that's because it's polarizable still, but also it has a negative charge. So it's like win-win. This is the best one on here. Then we get to this thing. Hopefully you recognize this terbutanol here. This would be like this. It's pretty big, right? It's big, it's bulky. Because of that, it's a poor nuke. Nukes like to be small. And last but not least, we have Cn minus. We kind of talked about that. That's a good nucleophile. All right. It is also extra good. You might not think about it this way, but this thing is it's very, very small, and it's linear, and because of that, it like can be like a little bullet and get right in there into the little spaces. So its linearity actually does make it a better nuke as well. Okay, so let's look at leaving groups now. Something that's going to be a good leaving group. Let me grab another piece of paper. Something that's going to be a good leaving group is going to be stable if it leaves. So if it pops, let me write that better. If it pops off of something, if what results is stable, then it has no problem popping off. And that makes it a better leaving group. Another thing that makes it is it's a weak base. So you look and see, is it a conjugate of a strong acid? So an example of that would be like I versus F. If we look at these two things and we're like, which one is going to be a better leaving group? You just pair them with their conjugate acids, make them a conjugate acid, HF, sorry. And you say which one of these is a stronger acid. This is a strong acid, this is a weak acid. So this would have a weak base, but this would be an incredibly, incredibly weak base. Its conjugate is a very, very, very weak base. And again, that's because this thing is a strong acid. It's your list of acids you should have memorized a long time ago, so I'm sure you guys got it now. All right, another thing would be if the leaving group leaves, if it can accommodate, I don't know another way to write this, can accommodate a negative charge. Well, that means if it can share that negative charge and distribute it throughout the entire molecule via resonance, I could write that, if it's got resonance, or maybe like an electron withdrawing group, to kind of spread the charge throughout the molecule, it'll be a good leaving group. The other thing is, again, if it's polarizable. As discussed, like I minus is better than F. That's because the electrons can move around. It's got a little more wiggle room to stabilize itself when it leaves. Okay, let's use this and see if we can answer the questions from the homework now. Or from the whatever this is. Worksheet. All right, so looking at these, we're asking ourselves, are all of these going to be good or poor leaving groups? So the first one, if we took this OH minus and we took it off like right there, we'd have a leaving group of H2O. H2O is neutral, H2O is super stable, and therefore this would be a great leaving group. Then we look at F. If F took its electrons with it, you'd have an F minus. F minus is not stable. In fact, it wants to immediately go back and react. And we know that F minus is a decent base as well, right? So it's not going to do much. This is going to be poor. And again, that's because it's a decent base. All right, here, if we took this leaving group and took it off, so that goes there, this would actually be pretty good. And the reason for that is we talked about how it can accommodate a negative charge. So we'd have this like OCO CH3 thing. We'd have this, right, if it left. And hopefully you can see that this would resonate. Those electrons can go there, those can go there. And because it can spread that charge out kind of between these two oxygens pretty well, it's actually going to be a decent leaving group because it is relatively stable. All right, then we have bromide. This would go here. We'd have a Br minus. We already know bromide's a good leaving group, but why is because if you took its conjugate HBr, this would be a strong acid, telling you that this is a very weak base. And it's a great leaving group. It's also relatively big, so it's also somewhat malleable as well in its electron density. Then we have this thing. So if this thing took off right here, or even the opposite direction, it really doesn't matter which leaving group leaves, or for example, if you don't understand what I'm saying, or if those went on there and this thing took off, no matter what, you'd be left with some kind of alkane thing, or let's say even this. And there's no way to really stabilize those electrons. There's no electron withdrawing groups or electron contributing groups particularly. Essentially, this is just an alkane. There's no resonance that can occur, and this would be a poor leaving group. Okay, both of them, whichever one you look at. Also, it's conjugate acid. Like if you took the conjugate acid of these, it'd be like this, which would be a pKa of 16, right? A pKa of 16 is not a strong acid. It's an okay acid, meaning its base would be okay, and therefore would be a poor leaving group. All right, let's consider this following reaction. Okay, so it says draw a mechanism with some curved arrows. So I look at this right away and I'm like, this looks to me to be quite a weak nucleophile. It's a neutral water, so this is a weak nuke. Okay, great leaving group, but weak nucleophile. And because it's a weak nucleophile, we're going to expect it to proceed via an SN1. So it says draw a mechanism, so let's go ahead and do that. We've got, so the first thing that happens is the leaving group will leave. So those electrons go there. And then we'll have this right here. Okay, they take the electrons with them. And now we can react it with water. These electrons are going to come in and attack right there. And we get this. Remember, anytime a neutral nucleophile attacks, you're going to be left with a positive charge. And then you could calculate that valence minus sticks minus dots. Get the formal charge of that is positive. Okay, now we know, and it's funny, we talked about this in class a few times, but your Cl minus that left up here can come back and grab this H. I've even started seeing that some books just write it like that, because they don't want to argue over what's grabbing the H. They just make the H leave. So you could do that as well, where the H just takes off. And then you're left with what we had here. Yay, go us. Okay. It wants you to draw an energy diagram. I didn't do a very good job keeping this first step down here, but essentially this would be a two-step reaction, right? Remember, the rate determining step is going to be when that leaving group leaves, and the next one would be after that. I still didn't do a very good job, but something to that effect. You'd have a two hump thing, because this is a two-step main reaction. We ignore this part right here, though it would be just a very, very small hump and results in a similar drop at the end. It asks for the rate equation because this rate, this is the slow step. Remember, the rate equation is only based on the slow step, the one that took the most energy, essentially. And in this case, this was the slow step right here. And it only depended on this amount of material that we had. So our rate would be K times the concentration of this thing. I don't know why I wrote that bracket. There you go. So another way that we would write this, and that we've been doing in class, is just calling this thing Rx, okay, where the R is all of this and the X is that Cl. All right, let's answer some of these questions. If the leaving group changed from Cl to I, what would happen? Well, from what we just talked about, if you have I as leaving group, it's going to be better. Its conjugate is a stronger acid than Cl. It's going to be a better leaving group. So if the leaving group is better, then that means this reaction wouldn't require as much. So it would be faster, or it would increase. Then it says the solvent is changed from water to acetone. So acetone is polar protic, or excuse me, polar aprotic, whereas water is polar protic, meaning it has an OH or an NH on it. And because of that, SN2 would be like more wanting to occur. So let me go over here. Let me draw this. I'm thinking of a better way to do this. So SN2, SN1. Just to remind you, SN2 prefers aprotic, and SN1 prefers protic, right? It was already in a protic solvent, and therefore SN1 would happen very easily. If we switched it to a polar aprotic, it would happen a lot slower, if at all, because SN1 prefers the protic, okay? So it would decrease. All right, and that just has to do with the stability up here. It wouldn't be able to stabilize this. This would be less stable, so it would take a lot longer. All right, the alkyl halide is changed from what it is, to this, where suddenly it's secondary. So here we have a tertiary, and here we have a secondary alkyl halide. So remember, for SN1 reactions, that tertiary happens faster than secondary, which happens faster than primary, which probably wouldn't happen anyway. So here, this one would be fast, and that's what we did. We started with a tertiary. This one would be slower. So if we changed it from a tertiary to a secondary, we would decrease the reaction rate. All right. The concentration of water is increased by a factor of 3. Well, our rate was only dependent upon the concentration of that Rx. So if we increase water, there shouldn't be any change at all. But in this next part, it says it increases the alkyl halide and water by a factor of 3. Again, water has no effect. That doesn't really matter. But the alkyl halide, if we increase this times 3, then our rate must also increase times 3. So our rate would increase times 3. All right. Moving on. So I think it's time, I think I'm changing this on your worksheet just because I don't quite have the time. I'm just going to change this to write the products. Hopefully there's plenty of other work to get the reaction mechanisms down. But before we do that, we need to talk real quick about when things prefer SN1 versus SN2, etc., etc. So, I'm gonna make a table real quick. So this is, let's go ahead and do, if we have a primary alkyl halide, secondary or tertiary, okay. And let's say when things react with what, and let's talk about which mechanism they preferred. Okay. So if you have a primary thing and so primary pretty much only is going to be, your choices are SN2 or SN2 or E2, right? But let's talk about the conditions for SN2. It will be an SN2 if you have like a really strong nucleophile. Hopefully that makes sense. Like if it's a weak base but it's a strong nucleophile, it'll attack via SN2. But if you have a strong bulky base, aka something that would be a poor nucleophile, like we talked about this in particular is usually the base that's used to do this thing. If we have a primary alkyl halide and a strong bulky base like this, it can't fit in and be a nucleophile, so instead it prefers E2. If you have a secondary thing and you have a strong base and a strong nuke, okay, so SN2 and SN1 can both do secondary. So when you're looking at something that's secondary, you need to look at these factors here to determine which one it's going to go via. So if you have a strong base and a strong nucleophile, that's going to go via SN2 or E2, because if it's a strong base, right, it hopefully makes sense. Oh, sorry, I didn't write base. If it's a strong base, hopefully it makes sense it's E2, and if it's a strong nuke, hopefully it makes sense it's SN2. If you have just a strong bulky base, just like before with the primary, you will only get an E2. And if you have a weak base and a weak nucleophile, then it's going to proceed via SN1 and E1, kind of like the examples we did in class. Okay, let me move this down. All right, now let's talk about tertiaries. If you have, for a tertiary, generally we want to do SN1 or E1, but let's talk about what might happen. So, or E2 as well, obviously. We talked about E2 prefers tertiary as well. So pretty much the only thing that prefers primary is an SN2. Okay, so with a tertiary, if you have a weak base and a weak nucleophile, those are situations that dictate an SN1 and an E1. These were the examples we did in class recently. But if you have a strong base, just to remind you, this is when it wants to go E2. Okay, so if you have a strong base, it'll do E2, weak base, weak nuke, etc. Generally, the way the two strong bases, what we've seen a lot of is OH minus would be like a strong base, and H2O would be like the weak base. But I'm about to give you lots more examples so we can kind of see if we really understand this. All right. So again, we're just going to write the products for these reactions, but we kind of have to use what we just discussed to determine which one's going to proceed via which. I look at this very first thing and I recognize, remember the K goes away and this is a negative charge. This is that tert butoxide that we've talked about over and over and over again. So tert butoxide is bulky, good base. If you have a bulky good base, that means it proceeds via E2. Okay. It is in, you can see this right here. It happens to be in a polar protic solvent. E2, even though aprotic is preferred, it can handle a protic solvent. So this would proceed via E2. So we'd get, I'm not going into the alpha, beta, and all this stuff. Oops, I should probably get the fact that it's cyclopentane. You would get that. Okay, I guess I will. Alpha, beta, and you would get this, where this would be your major and this would be your minor. Moving on, here we have a Br minus. Br minus is a very poor base, but it's a decent nuke. It's a poor base again because if you added its conjugate acid, if you looked at HBr, you know that this is a very strong acid, therefore Br minus is a poor base. Okay, so what that means is this will occur via SN2. SN2, we know, oh, gave you the answer. Ah, that's funny. So hopefully I'll erase that from your worksheet. So if it occurs via SN2, which means, remember that SN2 only has the backside attack. So the nuke will now go on the wedge, whereas before it was on a dash. Or vice versa. Okay, this next one. Okay, y'all, so I am back. Sorry, I had to teach a class, and I also didn't really like this question, but I'm gonna go over it to the best of my ability here. And I think that the reason I didn't like it is because we know that this CN is a really, it's not a good base, but it's a great nuke, right? We talked about it being linear. So it's a great nuke, but it's a relatively poor base, or weak base, maybe how we should say it. Okay, so it's a great nuke and you want it to like come in and hit this thing right away. But the problem is it's in polar protic solvent. We know that because it's got an O to an H. So remember, polar protic solvent kind of reduces the strength of nucleophiles. It kind of switches them around. So instead of being a great nuke, now it is a poor nuke, if that makes sense. Again, that's because it's in protic, polar protic solvent. So now essentially we're looking at it as though it is a poor nuke and a weak base. So as a poor nuke and as a weak base, we know that poor nukes and weak bases would proceed via SN1 and E1 reactions, right? So if we do it via SN1, although this is this is not a chiral center or stereogenic center specifically, it has it on a wedge, so it kind of is just saying, hey, I want to know what this would come out to be. So you would get, remember, SN1 attacks via front and back, so you'd get the CN here, and you'd also get the CN on the dash. For the E1, you would just get the one. As far as I can tell, you can only get one product out of this, which is that. You could have also put the line up here. It would have been the same thing. So don't forget, especially if you have a really great nuke, to look and ensure that it's not in polar protic solvent, because if it is, that makes it a weaker nuke, and that's going to switch things up. Okay, on to this one. So let's see, here we have a tertiary bromide. All these others have been secondary, right? Now we're at a tertiary. I know tertiary can pretty much only go via SN1, right? Or maybe E1 or E2, depending on the rest of the situation. So it's going to be one of these three. So let's talk about what we have. So this right here, it's a neutral thing, so that makes it a weak base. That automatically tells me it's going to be E1. It would also be a weak nuke, making it definitely SN1. So those are going to be the two methods by which it goes. Okay. So for an E1 reaction, or excuse me, for an SN1 reaction, remember the leaving group would leave, then this oxygen is going to come in attack, then the H is going to go off. We'll end up with an O, and then it's got 3 carbons on it, like that. So this would be, again, this one's via the SN1. And then when we do E1, remember, the leaving group's going to leave, and then it's got to take a hydrogen from one of these methyl groups. All of these methyl groups are equivalent, it doesn't matter. You'll end up with something that looks like that. All right. Moving on. All right, let's do all the possible products, the possible major products and the stereochemistry. So NH2. So this is going to be an NH2 minus, right? An NH2 minus is a pretty decent, is a great nuke. And it's a pretty decent base. Okay. I do notice that this is methyl iodide though. So essentially it's just a CH3 attached to an I. Okay. So we know it's a great nuke, and we know this is a methyl iodide, so it's primed for going through SN2. Right? So let's do that first. Let's do the SN2. So, and when SN2, remember this NH2 is going to come in there and attack this. The I is going to leave. So we just get to that. Okay, that would be our SN2. But then the other question is, would E2 happen? Because that should be your next question. But if we go to do, and by the way, this is a protic solvent, and you should have all these solvents memorized. Would E2 happen? Well, that's a great question. If an E2 occurred, remember we have an alpha carbon here, but do we have a beta carbon? There is no beta carbon, so E2 cannot occur. Again, that's no beta carbon. Because there's no beta carbon, you can't have an E2 happen. So this would be our only major product. All right, let's see. Then we have this one. So here we have a secondary. We have a polar protic solvent with a good nuke. And also a good base. Okay, and we kind of have to look at this in one very particular way. Okay, so anytime you have secondary, you already know that if it's SN2, right, we know that it prefers the methyl is greater than primary, which is greater than secondary, and tertiary won't happen. So this is like a last resort for SN2. It will do it if it has a great nucleophile. But here we have NH2, which is a fantastic base. It's great. It's a weak base, but it's a great base. It's looking forward to grabbing an H, and then it'll be NH3, which we know NH3 is also a base. So it even has a whole hydrogen to go. This is a great base. Okay, so you're looking at this thing in two different ways. You have a good nuke, but it's a polar protic solvent. So those two things automatically kind of like cancel each other out, right? Polar protic solvent, good nuke. You're thinking maybe it could be SN1, but the most important thing is you have a very strong base. So the only thing that can happen is this thing is going to come in and grab a beta hydrogen, okay? So I'm going to kind of go through that one more time because I know I did a bit of a poor job. Okay. We look at this and we say it's a good nuke and a good base, right? So you kind of want it to just go via SN2 and E2. But then you see it's in polar protic solvent. Polar protic solvent no longer makes this a good nuke. That's like off the table now, okay? So you're thinking, okay, maybe it's SN1, right? But an SN1 requires a really, really, really weak base, or a really, really weak nuke. This is not a weak nuke. But it is, however, a very, very, very strong base. And so this good base is going to come in and it's going to grab the alpha hydrogen here, or excuse me, the beta hydrogen here. This would be our alpha. You're going to grab the beta hydrogen here and then knock it off. And that's going to happen via E. I'll do a better job drawing this. That's going to happen via E2. Okay. So you end up with just that. All right. Hopefully that made some sense. If not, just go listen to it again, because I think I said it well. Okay, so now we're on to this thing. We have N3 minus. N3 minus is a good base, or excuse me, a good nuke. It's a great nuke. It's small, it's condensed, it's got a negative charge, but it's not, it's a kind of a poor base. Okay. The conjugate of this thing is actually a relatively strong acid. So if we added H to this, HN3 has a pKa, I don't know, it's like 4 or something like that. It's pretty decent pK, pretty low pKa. This is polar aprotic. So we know it's not messing with anything. This is supporting an E2 and an SN2. So again, we have a good nuke. We have an aprotic thing, and it's a poor base, so that really lends itself to an SN2. Remember, an SN2 is going to occur backside, so you'll get the shift from the wedge to the dash. All right, next, one of my favorites, because this is so recognizable now. Hopefully you see it and you're like, dude, that's a bulky base. It's a poor nuke because it's bulky, but it's a great base. And anytime you see this, you're gonna just think E2. Okay. So we're gonna occur this will occur via E2. And you're gonna get that as a major product. And that as a minor product. All right, moving on. Ooh, we're getting through it. Okay. So here we have water. We see water and we immediately think weak nuke. It's a weak base. Okay. So it's gonna kind of be crappy at any of the twos, at E2 or SN2. So we know it's going to be SN1 and E1. There's no other information around. This is secondary, which is telling you that it can happen. So let's go ahead and proceed via both. So SN1 and E1. With an SN1, we'll just draw what we had already. And remember that in SN1, you do back and front side, so you'll get 2. You'll get a racemic mixture, so you'll have the nucleophile here. And the same thing, but this time it'll be on a dash. Like that. So wedge and dash, nice little racemic mixture. And then over here for our E1, if this is our alpha, our beta 1's going to be right here, and our beta 2 will be right here. So beta 1 here and beta 2 here. So we'll get dash, dash, dash. Now this methyl group right here, because we're going to put it right there, that methyl group no longer has to be on a wedge because it's now sp2, so it's trigonal planar geometry right there, plus the minor product where you can keep this on the wedge, and it would be this. So this is major and this is minor. All right, last but not least, I spot a strong base and an okay nuke in a aprotic solvent. And this is secondary, right? Oh, I don't know, it already gave you some answers, but let's do this just to make sure we're cool with this. So a strong base and an okay nuke means it's going to go ahead and proceed via SN2 and E2. Now, if this had been an okay nuke with a protic solvent, it would have not done SN2. It probably would have done SN1. And I don't think that's something that we have enough examples of. So that's kind of why I'm saying it. Here we have an okay nuke, so it's just okay, but it's an aprotic solvent, so it will proceed via SN2. However, if it had been protic solvent, polar protic solvent, it probably would not have proceeded that way. I would have done SN1 or just E2 because this is such a strong base, the base will win. So what we get here is what we already drew, where we got just the backside approach, so we'll have just a dash instead of a wedge, and then our OH will be on that. So that's our SN2. And then our E2 results would be the most substituted one there as our major, and this one would be our minor. Woo! They don't end, y'all. They just keep coming. Okay. So here we have a weak base and a weak nuke. Anytime we have just a weak base and a weak nuke, we should be like, oh, yay, the ones. And so this will proceed via SN1 and E1. So our SN1 product will be a racemic mixture. And our E1 will be this. Okay. Then moving on to this. All right, so this is one I've been kind of looking forward to getting to because I think it's a good example. All right. So when we were talking about nukes, we said stuff with sulfur tends to be very good nuke, and selenium, this is a great nuke. But it's not really a great base. Remember, a great base would be like if we have something like oxygen here, etc. So something that's more polar, really attracting that H. So this is a great nuke, but this is a poor base. DMSO is aprotic. So we have a great nuke, we have aprotic solvent, therefore we're like, dude, this is probably definitely gonna go via SN2. And so we'll get this. The wedge was never touched, so it might as well stay there. And we had a carbon up here, and then this is this S right here, and then the CH2, CH3 attached to it. Okay. All right, now let's keep going. Oh, I spot it. Do you guys spot it? I see a bulky, strong base. It's an aprotic solvent, and it's got a temperature there to scare you. Okay, doesn't matter. We see bulky base, and we immediately are like, oh, we know a bulky strong base is going to go via E2. Okay. So with an E2 reaction, okay, so we have that there. Then we have these two methyl groups, like there and there. And then we're gonna have to put a double bond there as our major product. And we'll have another one that looks very similar to that, except it will be there or on the top one as our minor. Okay, on this next one, this is weak. This is a weak base. This is a weak nuke. We've come across these over and over again at this point. So weak base, weak nuke. We know that's going to go via SN1 and E1. Our SN1 will give us the racemic mixture. where we have OCH3 and that. And we'll also get the E1, where we have our most substituted one there. And our less substituted one there. So we got our major and our minor. All right, these next two questions, I didn't use them because they were things that we haven't gone over yet, but we will go over in the next chapter. Okay. So next one, we didn't use this because we didn't talk about alkenes and the splitting that occurs there. But so it says how many unique hydrogens are in the following compounds. So hopefully you agree this and this are exactly the same. So we'll call that A and A, and these groups here B and B. So now we're talking about NMR, so it'd have two groups. Here we have one, then this and this are the same. So A, B, B, C, C, D, and E. So I count 5. And then over here, we have, let's see, so these are all going to be different because there's no, like this one is not the same as that one, right? Hopefully you can see that comparing these two things. This one is between these and this has carbons between them. So they're all different, A, B, C, and D, and I get an answer of 4. Okay, and last but not least, we move on to my favorite, NMR. It's so cool. Okay, so it gave you some information about this thing. I honestly didn't use it, but there will be times when you're going to want to use it, especially if you have like an oxygen in there. For now, I can just tell that this is alkanes, and we know that alkanes are helpful in determining this, but we can also figure out alkanes from C5H10Br2, the degrees of unsaturation. Remember, if we had C5, if it had 0 degrees of unsaturation, we would have an H. You take 2 times 5 and then you add 2 of 12, right? Now, if there's 0 degrees of unsaturation as well, each bromine kind of acts like a hydrogen. So in total here, between hydrogen and bromine, you have 12 things. So therefore, if you have 12 things and you would have expected 12 things, this is 0 degrees of unsaturation. Cool. In other words, this is just an all alkane. All right, so let's start putting this thing together. Okay, it's got 5 carbons. You're gonna have to put 12 hydrogens on it somewhere, or 10 hydrogens, excuse me, and 2 bromines. So there's lots of different things it could be. I'm not even gonna start drawing them because with 2 bromines, those could be anywhere. Instead, what I wanna look for is the thing that's like got just a single peak. The reason I'm looking for the thing that has single peaks because that means it's a thing that has no neighbors, right? It has no neighbors. And if it has no neighbors, that means it's all alone. So this is a CH3 because it said it has 3 hydrogen. So I'm attaching to that to a carbon that can't have any neighbors. So I don't know what else is going on to this thing, but I know that it can't have any hydrogens on it, okay? So the thing that's next closest to it is this thing right here. And this is looks to be a CH2 with another CH2 attached to it because this is a CH2 and this is telling you that it has 2 neighbors. In other words, another CH2, if that makes sense. So I don't know what's going here yet, though I can guess pretty quickly because it's so far downfield. I'm like, this one has to have at least 1 bromine on it. And then I go to this next one right here. Again, this is a CH2. And I know that its neighbor has to be another CH2. And those are shifted relatively far downfield. Now, if you look right here, this this first one was also, you know, pretty down here. So I'm gonna automatically assume, knowing that this one had to have just one peak, right? Because it had no neighbors, that there had to be a bromine on this as well. That's the only way to have this thing alone with no neighbors over here. Okay. All right, so, but let's keep going. We can always change things if we need to. So once again, we had the single peak telling us there was a methyl group with no neighbors. So I attached that to a carbon and I threw the 2 bromines on there. And then I know that that's attached to a CH2. This is known, that I have a CH2 to another CH2. I can tell all that information from this right here. Now I'm on this CH2, which is probably this one. This looks to be like, it's got a 5 peak. Right, 1, 2, 3, 4, 5, 6, nope, 6, that makes even more sense. Okay. And what that tells me is this thing has 5 neighbors. So I have some CH2 thing with 5 neighbors. That's this one right here, and it has to 5 neighbors. I already have 2 here, so that means this must be the other 3. You can go back and check. You can say, okay, now this, if this is this methyl group right here, I know that it has to have 2 neighbors. And that would be this and this, okay? So I think this is the final structure. It wasn't too horrible, right? So especially if you can find a single peak, it makes things really easy, because you're like, dude, I know that that thing has to have no neighbors. And so you know that there's going to be at least 1 carbon with no neighbors on it, if that makes sense. Or there's an oxygen, but that wasn't the case because we knew the formula to begin with. So, all right, guys, I hope that helped. And is that everything? Yep, that's everything. Have a great day.